junk. The SMOS satellite was launched to measure soil moisture and salinity, and biomass was a noise because vegetation contains water, so it emits microwave as well, but it was considered as a parasite, if you want, to the soil moisture retrieval. But in fact, Jean-Pierre Vigneron realized that you could get something about the biomass, and we provided the first map of biomass change over the last 10 years, which has been the object of a lot of Nature papers, because of course it's a unique product where you see the carbon gains in green and the carbon loss in red. Then there was a PhD of Martin Schwartz, where we wanted to create a map of biomass, and we realized that the best proxy is height. And fortunately, height is measured by a spaceboard LiDAR called JEDI. It's a fantastic instrument. It's standing beams, basically, and it's recuperating the rebound of photons at different height between the ground and the top of the canopy. I think you have seen Martin's defense. It's in fact the equivalent of 4 lasers. So it's great. It provides height on footprint. The problem is that still it's a discontinuous sampling. It's like a super inventory. You have a lot of points, but still you have gaps between the points. So the PhD of Martin was to basically say, I have some sparse labels from JEDI. I'm going to put as an input of a deep learning model some continuous field from like Sentinel-1 radar image or Sentinel-2 radar images. And I'm going to fill the gap between JEDI using and UNet was derived from medical imagery. It's super flexible. You have typically, if I had to do a linear regression, like I try to say y is JEDI and x is Sentinel-2. I would do y equal ax plus b, and I have a and b. Okay, so that would be 2 parameters. Instead of this, it's not really regression parameters, it's more a kernel of the UNet, but you have 17 million of A and B. You are going to tell me it's crazy. How can you fit 70 million of parameter? I keep in mind that the number of data you have from JEDI is more than 100 million, and the number of data of pixels you have as input data from Sentinel is something like maybe 1 billion or 500 million. So you are still not, let's say, overfitting by trying to ask this model to find 70 million of, let's say, regression coefficients. So Martin made some very nice map in Leland, then some very nice map of height at 10-meter resolution for France, and he made a map of biomass. It works like this. This is the forest of Crécy, and I'm stealing all your plots. So you see the JEDI data is good, but with human eyes, you see, yeah, there is some kind of light color, which means tall forest, but in between, we would like to see that in the center of the forest, it's tall forest, and at the edge, it's small forest, but we don't really know. And of course, after the application of the UNet model, wow, you get a super map, and you can still see that in the center, you have some tall forest, but it has some kind of gaps and some holes that are probably reflecting degradation. So it's impressive, but how good it is, and for this, you need validation data. So Martin has used the height, which is measured at forest plot, and also on the LiDAR, airborne LiDAR, and he found that there is a good correlation. It's not perfect, and you can see still for the very tall trees, model underestimates the height, but it's quite good, and the mean error is about 3 meters. You can say 3 meters is good, but how good it is compared to our competitors? There are a few people who have done such exercise. Potapov, he used the Landsat instead of Sentinel, and he used a random forest. Lang, he used only Sentinel-2, but he used the UNet, and he applied it globally. And there was also a work with some planet data. So visually, it looks like that. The Potapov looks very different from our map on the left. Lang, it looks similar, but it's more fuzzy, it's more blurry. And the planet data, they don't have as much contrast. So which one is good, which one is bad? Fortunately, you have some independent validation data, so you can really judge, okay, which one is good. And obviously, the Potapov map from Landsat done by the US colleagues, it has absolutely no correlation with the real, like the observed height at the site. The Lang map is not too bad, 0.3. The planet map is a bit better, but the Schwartz map at this site is better. So why are we so good? Well, maybe because it's a better deep learning architecture. Maybe it's because we put Sentinel-1 data instead of just optical data. Maybe it's because, well, you know, you are French, you work in France, you spend all your PhD, so it's a local model if you want. And it's easier to ask, let's say, a regional study to be accurate and to work on this very hard, rather than to do that for the global product. I'll come back to this later. So some applications, then we have a lot of papers. We looked at the fire polygons and we found out how much biomass was lost in the mega fires in Leland in 22 with the Lilian Valley. There is a PhD student who is not yet using the map, but is using basically forest disturbance polygon. And the big question is, what is the cause of the forest perturbation? So he's using also some kind of machine learning model called DBScan with the GraphNet network to try to put a color, which means a cause for each of the observed forest disturbance. Most of this is harvest, but you can also see some fire, some insect attack, and some biotic dieback. And this has never been done before. Very important. Then another application is that if you have your height or your biomass as a map, and if you have a map of the previous forest perturbation, so when the forest was cut or burnt, you can parse them into a space for time. So you take a small region, you say, well, 20 years ago, there was no forest, and now there is this biomass. Then the same region, 10 years ago, there was no forest, and there is this biomass. So you can derive something which is very important. It's called a growth curve. So it shows you how the height of the biomass grows back after a plantation or a disturbance. And this is very important because it gives you first the potential for carbon sequestration. So there are a lot of papers in Nature that look at the carbon sequestration potential per species. So it gives a lot of information about management. And it can be used for extrapolating the future of the forest. So in this paper, which is in review in Nature by François Ritter, he used this approach of recovery curve to basically build a model where you read the past destruction of forest, and after each destruction, you have a regrowth. So you can do basically a forward-looking simulation where you can predict in 2030 which region of Europe will be continuing to gain carbon. It's the dark purple areas, which regions are going to lose carbon in yellow. And then we make a projection. And as you can see, we predict that first, our model is matching extremely well with the forest inventory. We calibrate only one parameter, so it's a very good model. And then we predict that basically we are going to be completely away from the target of the EU, even if we plant 3 billion trees. So 3 billion trees is a ridiculous.
Recording in progress.
And we would need kind of provocative part of the talk is that we would need to accept to decrease harvest by about 23% if we wanted to match the carbon objective. Otherwise, we continue the harvest, and of course, we will be on the target for the sink. To finish with, Martin did also some height change products. So this is unique because instead of having a static map, you can look at change. The red area, it's a difference between 22 and 27. The red area are the forest plots that have been cut, but the green area, and this is very interesting, are the forests which have been growing because they are young. Then with a lot of GPU, you can do global products. So we have a number of national products for France, for Ghana, for Spain, for Congo, for the Amazon. Now it's global. So there is, for instance, for this large African project, with Kairos, they applied our model, and we have a full map of the biomass and forest height over the entire Central African forest, which works also very well. And with colleagues from Ulster University, they have a lot of GPU. They train a UNet model. I think they use 3 GPU to train a model for 1 week. And then they have a lot of, they have stored all the Sentinel-1 and Sentinel-2 image. It's enormous. It's something like, I think it's 40 terabytes of data. So they need very fast accessed disk on their supercomputer. And then they do the calculation of height, and they have a global height map. So the world has changed, because before, if you wanted to do that, a 10-meter product with a deep learning model, you need 100 researchers and a big AI lab. And now, basically, a grad student in a machine learning department, in 1 week, he can do a global map. So it's changing a bit the perspectives that we had before. Okay, I'll let Ibrahim speak, but with the planet data that I advertised, this is, for instance, a region in Africa. So with bodies, you see those things. With Landsat, some structure, and with planet, wow, you can see the shrubs and the fields. Another region in Germany, okay, with Moody's. You know where it is, you don't know. With Landsat, you start to see things, but you're not sure. And with Planet, you see it's a motorway crossroad, and you have some tall trees and some small trees. So with the Planet data, you can do higher resolution products. So with colleagues from Denmark, we have a map of biomass and height and tree cover at 3 meters over the entire Europe. And this is interesting because we discovered basically all the trees which are outside forest. And in some regions like Brittany or Normandy or UK, where the forests are very fragmented, we found that you have 25% of the tree crown cover, which is not in official forests. There are hedgerows or gardens or, road trees and so on. So trees outside forest are important. We did a tree counting of all Denmark, this time not using satellite, but using very high resolution airborne image. We had this paper in Nature, it's the same thing with the world view images at 0.5 meter, where there is basically a segmentation of all the trees, and then with allometric functions, we can calculate the carbon of all these trees. Same thing for Rwanda, even with the change, also with airborne photos. And the last paper that was published last week in Nature Sustainability by this group, it's also quite a performance. We use the Rapid Eye data, which was the precursors of Planet, and the Planet data. And we look at all India. India is the largest country in the world for agroforestry. And we look at the large trees, because still 3 meters, you cannot see shrubs, right? And we make sequence. We calculated the trees that have disappeared in those landscapes. So all the purple dots are large trees that disappeared between 2018 and 2010. And we found that no less than 40 million of large trees have disappeared in Indian croplands. And we wanted to understand why. So we had some kind of interviews with villagers and rural communities. We thought it was drought, but no, it's not drought. It's just because they buy machines. They want to harvest, and they cut the trees to get through with the machines like we do in France. So it's a bit of a problem. It doesn't mean that the trees are disappearing in India. It just means that the large trees are cut and they may be replaced by small trees. Okay, and I'll leave the floor to Ibrahim. Maybe we can take questions afterwards.
Thank you very much, Philippe, for the quite
and all the data are publicly available.
for this very interesting talk and the comprehensive coverage about this subject.
And one of Ibrahim will be more.
Yeah. So, does anyone in the room or online have any question to Philippe?
I have one question.
Yes, please.
Like, if there is a region, and even if there are 2 or 3 trees, will they contribute to carbon sequestration, or do you always need a larger area? And
Well, of course, if you, in terms of area, these trees outside forest, in France, they represent 1% of the total area. So even if their growth rate was, let's say, 2 times bigger than the growth rate of trees in forest, they would increase the carbon sink by 2%. So it's not like we are underestimating by 30% the French carbon sink because we ignore the gardens in Gif-sur-Yvette. But still, they are important because you see in Gif-sur-Yvette, typically, you have a lot of trees. Huh? It's famous for that. And they are not counted in the forest inventory, but they are storing carbon, and maybe they are growing and they are also increasing the carbon sink. So having a better idea of what are the carbon changes in this kind of isolated tree is important. It's also important because the farmers in France, they are given subsidies to plant hedgerows for erosion and biodiversity. But generally, they take the money, they plant a hedgerow, and 5 years after, they don't have the hedgerow, they cut it. So if you have satellites, you should be able to monitor basically if they really receive the money to plant some hedgerow trees, and then they left it in place, or they just remove it 5 years later. So that's also kind of application you can have.
What you show is mostly for the above ground biomass.
Yeah.
So what happened to the below ground? I mean, did you see that there is a, because for instance in India, when you cut the tree, obviously you remove the above ground biomass, but what happens to the below ground biomass?
It's a good question. Well, below ground biomass, if it is dead, it decays. If it is wood, it decays with a certain time scale, which is typically 20 years for kind of wood to decay. If it is fine roots, like below ground, but fine root biomass, then it decays in 1 year. Huh? Okay. It's like leaf litter, if you want.
Okay.
But generally, if we want to make a map of below ground, there are some, let's say, magic ratios called expansion factors. And there is even machine learning map of those below ground to above ground ratio. So it's relatively piece of cake to go from an above ground map to a
Yeah, using some hypotheses. And what is the ratio? I mean, it's
20%, but it depends. If you have, for instance, arid conditions, shrubs, they invest a lot of carbon in below ground. So shrubs, they can have 60% below ground biomass.
Okay.
The typical forest here, it's maybe 20% is a good number.
Okay.
But it's dependent. If you take, for instance, oaks, they are kind of, their mindset is to do deep roots to penetrate deep in the ground. So they need pivotal deep roots to sustain the wood and the water, but it's mainly for mechanical reasons. So the oaks, they have much more below ground woody biomass than the spruce, because the spruce, they are lateral roots. They don't like to do deep roots, they prefer to do surface roots. So depending on the species, there are different life strategies, and the below ground to above ground is slightly different.
Maybe, are you ready or?
Yeah, let's go.
So, if you are ready, we could maybe.
Recording in
So if we can
And speak soon.
so if a part in is ready, we could take other questions after the presentation. Okay.
Yeah, okay.
Some time to you.
Okay, so my talk will be a little bit technical. It's about the contrastive learning, which is a subfield of deep learning. So I will not be talking about the particular model in deep learning, but just a new framework to train deep learning models in a non-supervised manner. So why we are interested in contrastive learning or non-supervised learning for deep learning models? Because as Philippe showed you in the examples in his presentations, to have a meaningful product with deep learning models or deep learning frameworks, we need three components. The first component is the input data that we are using, or the data that the model will take, which in our case are satellite data, and these we don't have problems with. We have a lot of data, and satellites are acquiring terabytes of data each day. So this is not an issue. The second component are the deep learning models which we use, and these also are not an issue. We have a lot of models, and they are made for a lot of tasks that we are currently interested in. However, the third component are the targets or labels that we usually need to calibrate our models to have a meaningful product. For example, to take that case of canopy heights, we needed Sentinel-1 and 2 images. We needed a deep learning model, which was UNet in the case of Martin. And thirdly, to calibrate this model, we needed JEDI data. Unfortunately, for the canopy height case, we have a lot of JEDI data, so it was easy to train this model. However, let's take, for example, the case of tree species classification, or if we wanted to estimate biomass. Usually, we will need the same type of data, which are Sentinel-1 or 2, or PlanetScope data, or whatever. We have the models, however, we don't have a lot of calibration data. For example, we have a new PhD student who's working on tree species classification, and basically she'll be using remote sensing data, a deep learning model, but she doesn't have a lot of NFI data. So one of the solution to our problem will be to train a model in a non-supervised manner, and then fine-tune it on the few labels that she has over these three species. So contrastive learning, as I said, is a non-supervised framework to train these models, and it's used to extract meaningful features from the images, to extract meaningful patterns, and then we can fine-tune it to whatever task that we need. So the presentation, we'll see what contrastive contrastive learning is, we will see the limitations of supervised learning, which is, for example, the case of canopy height estimation. What is contrastive learning? The intuition behind it, the learning objectives. So what does a contrastive learning framework actually teaches a model? Then we have, we will see the data that we use in such models. A popular framework, I will only talk about the simplest case, which is a model called SimClear, or simple contrastive learning representation. Finally, what we can do with a pre-trained model with this framework. So as I said, one of the reasons we might need contrastive learning in our work is that we have a lot of satellite imagery, a lot of remote remote sense data, and but we don't have a lot of labels. So we have sparse labels, and if we want to make use of all these advancements in the deep learning world, they won't be enough. Another reason, there's a lot of wasted efforts in what we are currently doing in the supervised learning fashion of training models. So let's say we spend a lot of months building this model for example, for the canopy height estimation case. So this model will be fine-tuned to extract features only relevant to the canopy height output that we want. However, if someone else wants to take this model with the data that it uses and train it, or to obtain other variables, for example, tree species or biomass or something else, he needs proper labels for this model to retrain it on, and he most likely will need to retrain the model from scratch. So all the efforts that we put on training this model for the canopy height case will be just lost. These are the points I talked about. So this is a case where I worked on a new also canopy height estimation model. So we have our training data. We have usually for these types of products, we need an encoder that will take the data, encode it, and then we have a decoder that will take the representation, decode it, and then we can calibrate it with GEDI data to obtain a canopy height. However, as I said, this model will only be good for canopy height estimation. It will not be good for other tasks. Unless we train it in another manner, for example, in a contrastive manner. So it can be used as a general model that extracts patterns from these data, and then we can fine-tune it to, I wouldn't say whatever we want, but a lot of the cases where the target data shares some similarities to the canopy heights. And finally, because I find it challenging and fun, so that's why I do it. So contrastive learning, as I said, is a way to take a model, compress it, data, compress it in a model, and we will obtain at the end a vector. However, what we want is that this vector needs to contain the most meaningful data within an input image. However, these models, since they are trained to extract the most meaningful features within the image, and usually when we pass to the fine-tuning task, we no longer retrain this model. So the that were trained or learned will be fixed. So we can no longer retrain them. And this can cause some, let's say, a decrease in accuracy in comparison to the classical case of supervised learning. However, this model can be used to for multiple tasks. So we can, let's say, a little bit of a trade-off between high accuracy but a very specialized model, or a more broad model but with less accuracy for the downstream tasks. The intuition the intuition behind contrastive learning is that to take, let's say we have the image on the left and we ask the model to find the most similar image on the right. So we as a human, if you want to find the most relative or the most similar image on the right from in comparison to the image on the left, we have to start comparing features of the animal on the left with all the animals on the right. So we have, for example, the animal has a pointed ears, and we can say, yeah, it looks like the ears of the cat. However, it's not a cat because it has the eyes of a dog. And it looks completely nothing. The rabbit, for example, or the tortoise. I think, yeah, it's a very easy example, but for a computer, it's not that easy. However, it turns out that telling things apart is a good way to understand the world, and we can also teach computers or machines to do the same thing. And so this is another example. So let's say we have the usual case of supervised learning. So we have our model predictive or a generative model that needs to generate new data. So it takes a data X, which is in our case remote sensing data. We pass it through a model, and then we obtain the data Y, which are, for example, canopy heads. In the case of contrastive learnings, we take data X1, for example, in the previous case, which was an image of a dog. Then we have data X2, which could be another image of either another, like, say, species of a dog, the same dog, in a different frame within the image. We pass it through a model, and then a model needs to know whether these images are similar. Is it the same type of animal, or is it a different type? And this is the learning objective. So in terms of implementation, let's imagine our input space are these three images. We pass them to an encoder, which is a type of model. Then we will obtain three vectors representing the compressed features of these images. And the objective is to close the distance between the vectors obtained from the encoder of the two similar images, which are the images of a dog, and then push away the vector representing the image of a cat. So in this way, when we want to apply our model, the vectors obtained from the encoder will be for a given species of an animal will be close together in the representation space. So the vectors coming from images of a dog will have smaller distances or high, let's say, similarity. But images coming from different species will have a very large distance or very low similarity between them. To train a model for that, so we were talking about data. So we have either the supervised approach, and in this case, we collect a lot of images. Then we have a labeler that needs to say that these pairs of images are either similar or dissimilar. And this returns us back to square one, where we need a labeler or someone who needs to label these large volumes of data, which isn't a very cost-effective, let's say, manner of doing things. So it's not a good idea. So what we need is a way to generate pairs of data from the same image in a also non-supervised manner. And for that, in the contrastive learning approaches or studies, they found that they can take a single image, do some augmentations to it, and these are geometrical or color transformations to this image. So I have the color transformations. And so our pair of positive pair of data will be this image and another one made of the multiple transformations. So for example, you can, in the first case, crop and apply a jitter transform to this image. Will be our view one of the image, and our view two will be, for example, translate the image and apply a blur function over it. So we transform the data, we change them in a manner that will still be useful when we pass these images to the encoder. So it's in a way forced to learn that these two images, while they have different or they have some differences in them, the model will still be forced to learn that they are the same. And so luckily they made a study and showed the most two best transformations to apply to these images in order to have a very good learning objective. And they found that the color transformation and the cropping of images are the best. And luckily this is also suits us since we are working with remote sensing images, and we can't for example, add noise to the images as they are already noisy. They are blurred since we are working with Sentinel-1 and Sentinel-2 imagery, for example. Rotating them wouldn't be that effective. However, we can take images and crop them a little bit. And for the color, we can play with the colors of the images since the color have a meaning, which is the reflectance, for example, or the radiometry if you are working with radar data. However, instead of changing the colors manually of these images, we can take images from different seasons. Taking images from different seasons will have different reflectance values. They will show different colors, but they will still be the same or the same thing. However, we can have a lot of differences. For example, let's see, if we talk about deciduous forest or coniferous forest or evergreens. So taking images from a different season will show different differences in the reflectance values, and each forest will have different different values based on which season it was acquired. So now how we can train this model? So we have our representation, and a representation is basically a vector which is the output from an encoder based on a given image. And we have the similarity metric between two images. And this similarity could be either the cosine similarity between the vectors, the Euclidean distance, for example, or the dot product similarity. These are the three similarities that we really consider. And so to train this model, we have our input images. We pass it to two random augmentations, which I just talk about color, let's say color changes, cropping, flipping, etc. So we will have two transformed images from the same input image. We'll pass it along the same encoder, which will give us two different representations at the early stages of the learning. Then we apply a projection head and maximize the similarity between these two vectors since they are coming from the same image. In terms of mathematical, let's say mathematical function that we use since we are dealing with deep learning, and when we say deep learning, usually we talk about the loss functions to that we want to minimize so the model can learn what we want it to learn. Basically, what we want, if we consider this as a similarity matrix, what we want is to have the very highest similarities on the diagonal, but very low similarities elsewhere. To do that, one of the loss functions is the normalized temperature cross entropy loss. It's a very intuitive loss, so it takes the similarity of two images from the same, let's say from the positive pair divided by the similarity from a given view and all the remaining images which are dissimilar to this image within the batch. We have the same image with the two transforms applied to it, divided by the same similarity of this image, plus the similarity within other images within our batch. And the only way we can reduce this loss function is if we force the model to maximize the similarity between the positive pairs and decrease the similarity between the negative pairs. And doing that for a lot of iterations will make our model, let's say, understand or extract the most meaningful features in our within our data. However, it won't have a, let's say, any meaningful output because it wasn't trained on producing anything meaningful. It will just understand more the patterns within the images. This is basically what's left of the loss functions. So after training this model, usually log the weights, and we apply some add to it heads for specific tasks. For example, let's say canopy height or biomass or tree species classification. And the advantages, as I already said, to have reusable models, so we can have the same model but with different objectives later. Usually, we for a given downstream task, we usually would need fewer labels than normally would need. And 3 fewer computational resources only for the task, not for the pre-training of the model. And lower training times also for the downstream. And finally, we can do also zero-shot learning, which is taking an image and comparing it to, so we have the encoder, we pass an image to it, we get a representation, and we can compare it to a database of vectors. In this case, the model will tell us that this image is an image of a cat, so we would have a zero, let's say, shot classification. So the model wasn't taught to understand the difference of the images, but by comparing vectors from vectors in a database with labels and vectors obtained from an encoder, we can do a direct classification of the image that we have. And that's it.
It's beautiful because with this model, for instance, if I can want to map 3 species and 3 height and the JEDI full waveform and 3 cover, and you can get these 5 things with a single model, which was everything. Super kind of performance for multitasking and problem with few levels. I guess it's very used in